Hi. In this new episode, we're going to try to show a brief proof of the Blackwell theorem or the Blackwell informativeness theorem, which is simply saying that there are three different methods that we can use to rank the information structures or signals. Okay, and in the previous videos, we have already introduced two ways, right? So the first approach is to use the expected utilities to compare two signals, and later we also showed that we can use the concept called garbling to actually establish the connection between two signals, right? And also it's also possible to further consider two signals in terms of the feasible set of the actions, and we will later show the definition of that, and also show the equivalence of those three different statements regarding the relationship of the ranking of the different information structures. So this is simply just the Blackwell informativeness theorem, provided by David Blackwell in 1951 and 1953. Okay, and also we'll show the statement of the theorem, and later we'll also show another a proof, a very interesting proof recently given by another researcher recently in 2017 by a researcher called Oliveira. So in their paper called Blackwell's informativeness theorem using diagrams. Okay, so we'll also show their idea to how to prove the Blackwell theorem differently. Okay, so now let's get started. So briefly, so this let's take a very short review of this decision problem. Okay, so we're trying to solve this decision problem under uncertainty, right? So that's why we need information here. Okay, so remember that we have this utility function u of a and omega, right? So this is the decision maker's utility, depends on the action a and the state of the world omega, right? So this agent or this decision maker doesn't know anything about this omega, but they can observe this a signal. Okay, so in this model, we don't care about who is sending the signal. Okay, but later, such as in the Bayesian persuasion problem, we'll consider a sender is actually sending the signal. Okay, but here we don't need to consider about that. So we only need to assume that this agent can observe this signal realization. Okay, this signal. Okay, so this signal is drawn according to some information structure, right? So, or this signal, okay, signal structure. So all those terms, they refer to the same thing. So this is a map from the state space to the set of all distributions over the space of the signals. Okay. So this is simply specifying the conditional probability, okay, of S given little omega. Okay, so the probability of observing the signal S if the state is omega. Okay, so this is the basic decision problem. So Blackwell in 1951 and 53. So in those two papers, so Blackwell showed that there are different three methods or three approaches to rank different information structures. Okay, so three ways to rank sigma. Okay, different. We can call this sigma, or previously we call this pi, right? So there's the same thing here. Okay, so remember that the first. So here we introduce the first approach as the garbling here. Okay, so to be in a more consistent way as the other paper. Okay, so we see that garbling. Okay, so sigma prime is a garbling of sigma if this decision maker knows sigma. Okay, decision maker okay, who knows sigma, then this decision maker can just produce or obtain a sigma prime, okay, by drawing S prime after observing this S, right? So it means that there must exist some function, we call this gamma, which is a map from S to the set of distributions over S prime, okay? And specifically for the sigma prime, okay, S prime given omega, so this is simply a summation over S, and we use this gamma function to multiply the sigma, right? And sum all the S's over all the S's, okay? And that's simply this. Okay, so that's how we use this garbling to describe a possible ranking between two different signals, right? So another possible way, so we are going to introduce in this episode, okay, we haven't formally defined this, but here we're going to define that here. So it is that we're using the feasible set of the actions. Okay, so formally we use this feasibility. Okay, feasibility. Okay. All right. So okay. So the set of actions A, okay, and this signal sigma, okay, all right, and given a mixed strategy, so it's called mixed strategy. So it must be a map from the space of the signal to the set of all distributions over the action space, right? So it's the mixed strategy here. So given those A and sigma, so this alpha actually induces a distribution over the actions conditional on the omega, right? So this induces a distribution over the actions, right? And this is conditional on omega, of course. Okay, so everything is conditional on omega. So then we can use this idea, this feasibility, to rank the sigma and sigma prime, right? So this rank is according to something that to see which one we can obtain a bigger set or larger set of the feasible conditional distribution of those actions. Okay, So we can rank sigma and sigma prime based on which can give a larger set of the feasible conditional distribution of the actions. Okay. All right. So that's the how we use this feasibility of those conditional distributions of the actions to compare to different signals. Right. So this is the second way, and this is the first time that we formally introduce this idea, this approach to compare two different signals. Okay. So the third or the last one. Okay. So we have previously already seen this, right? So it's to use the expected utilities to compare to different signals. Okay. So expected utility. Okay. So, and this is very straightforward. So if we say that sigma is more informative than sigma prime, if this agent who is acting in this Bayesian way, right? So use the Bayes rule to update the beliefs. So if this Bayesian agent can so this agent must be acting in the Bayesian way. Okay, so this agent can have a or can obtain a higher expected utility using the sigma rather than sigma prime, right? Obtains higher expected utility under sigma than those under sigma prime. Okay? So that's the third one is pretty straightforward. Okay. All right. So and together, right? So this is we can formally state the Blackwell theorem. Okay, the Blackwell informativeness theorem. So basically, it's essentially saying that those three approaches they are equivalent. Okay. So the Blackwell theorem, and we can explicitly write those again. Okay. So the first is that sigma prime is a garbling of sigma. Okay, and given any action space, right? So the action set. So the set of all the conditional distributions over the actions which are feasible. Okay, given the sigma. So this set has to contain those that are feasible under the other signal sigma prime, right? So the set of all conditional distributions over the actions that are feasible under sigma. So this set has to contains those distributions over the actions that are feasible under the other structure, information structure, sigma prime. Okay, so that's the way. That's the second way to use the feasible set. Okay, so the third one is the special utility. Okay, so if this agent is acting in a Bayesian way, then this agent has a preference of sigma over sigma prime, right? For any kind of similar decision problem in this structure. Okay, so this is essentially the Blackwell informativeness theorem. Okay. All right. So next we'll use the we'll introduce the proof. Okay. From okay, let's write this paper's title. Okay. So it's Blackwell informativeness theorem using diagrams. Okay. So this is a very interesting idea and a very interesting approach to prove this famous theorem here. Okay. So the author here. Okay. In 2018. Okay. Go. Let's together to try to understand how they're using the diagrams, okay, and the ideas of stochastic maps to show the equivalence of those three statements. Okay. So before the proofs, let's take a look at those concepts, the backgrounds, and how they are using the stochastic map to represent those key ingredients of those statements. Okay. All right. So let's say we have a finite set X. Okay. So right. So we use delta X to simply denote the set of all distributions over the X. Okay. And we say that a stochastic map, okay, stochastic map between two finite sets, between X and Y, and this is simply a function alpha from X to the set of all distributions over Y. So that's it. Okay, so that's a stochastic map. Okay, very simple. And we introduce another concept called composition. Okay, so if alpha, okay, we already have this. So alpha is a map from X to delta Y, and we define beta is a map from Y to delta Z. Okay, big Z. So the composition of two functions, or the composition of those stochastic maps, beta compound alpha, okay, then it's simply a map from X to delta Z. Okay, so that's it. Okay, and specifically, this is defined, right, as follows. So this is probability of Z given little x. Okay, so those are the values of those random variables, right, using the lower cases. So this is a summation beta Z given Y times alpha Y given X, right? So this is a summation over all the Y's. Okay, because we're summing over the Y's and we don't have any Y's here, right? Okay, so that's simply the definition of the stochastic map and a compound between those two functions. So this composition is, of course, associative, right? So the order of the summation between three of them doesn't matter. Okay, so if let's say we have, okay, as for the example given in our paper, so we have this gamma is a map from Z to W. Okay, so this is not omega, this is big W. So if we compound gamma with beta and compound alpha, so it's the same as gamma compound beta compound alpha. Okay, so this is associative. Okay, and specifically we sum over, okay, we'll write that later. So it's little gamma W, okay, given Z, beta, Z given Y, alpha, Y given X, and we sum over all the Y's and Z, okay? So the order of those summations, they do not matter, okay? So this is associative. Okay, and another important concept that we will use in the proof shortly that we have to introduce here is that a kind of a special stochastic map is the identity map. Okay, given by this their paper here, and this is a very interesting definition. So, okay, it's called ID of Y. It's a map from Y to the set of all distribution over itself. Okay. So it takes this point, this Y, and to a measure. Okay, and this is an element. This measures an element of the set of all distributions over this set itself. Okay, and that this simply gets the probability 1, gives the probability 1 on the little y, okay? And we'll use this. This is quite useful in the proof later. Okay, so, and this identity map, okay, this is has a very important property, and which is that given any maps, okay, let's say the so this identity map, it is quite important. So this is because that if we have two maps we just defined here, okay, alpha and beta here, okay. So if we have those identity map, then for sure we will have that ID Y compound alpha is alpha itself, okay, and beta compound IDY is beta itself, okay? All right. Because here, notice that we have those Y's here, okay? And this is how we define those terms correspondingly. And those are very important details. Okay, good. So this identity map, and also we have the associative property, right, for the composition. Okay. Okay, so we have those things together. So together they make this stochastic maps as a so-called category. Okay. Okay. So, and simply this category, we don't have to give the specific definitions, and simply it has those properties that we just show. Okay, with which is the identity map and the associativity. Okay. So later we'll use those idea of the stochastic maps and this category theories to prove the equivalence of the three statements in the Blackwell theorem. Okay, so in the category theory, it's often to say that we can represent the stochastic maps as some diagrams. So we use little arrows to connect the nodes. Okay, between those nodes which are just the finite sets that we just showed. Okay, and we say that those kind of diagram, they commute. Okay, so if any of those two path with the same beginning and the end, and define the same stochastic map through the composition. Okay. So to give a straightforward illustration of this commute, okay, let's simply draw a little diagram here. Okay, so let's say a finite set A. We just use those little sets from A, and we have alpha, right, to map to B, and use beta to C, and alternatively, okay, we have alpha prime from A to B prime, and have beta prime from B prime to C. Okay, so this diagram commutes. Okay, so this commutes. So this is essentially saying that the composition of beta and alpha equals to the composition of beta and alpha prime. Okay. So that's it. That's the how we define this idea of the commute. Okay. And interestingly, after we show those concepts, and we realize that all those information structures, or the garblings, or those mixed strategies, they're all stochastic maps, right? So, and then we realize that actually the first statement in the Blackwell theorem using the garbling, right? So the first one, we can restate this as follows. Okay. So there exists a stochastic map, gamma, okay, such that gamma sigma prime is the composition of gamma and sigma. Okay, so this is simply defined by a stochastic map. So that's it. And using this category diagram, so we have the state space maps to signal space, right, by this signal structure. And accordingly, if we have this garbling as prime, right, so we have this garbling sigma prime, then we can map to this S prime, right? So where is this gamma function? So it's simply this, right? So this is gamma. So this is very straightforward and very interesting way to see those results using the diagrams and the category theorem provided by this researcher, okay, by this study. Okay, so and similarly, right, so this is garbling, and similarly we can define the feasible set, or actually we define this the conditional distribution over the actions. okay, induced by a strategy alpha. Okay, so conditional distribution over the actions. So this is induced by a strategy, mixed strategy alpha. Okay, so this is simply alpha composition with sigma, right? Okay. So then the second statement can be restated as follows. So for any alpha prime, okay, so there exists alpha such that we have a following diagram that commutes. Okay, so this diagram is simply as follows. So we have our state space. Okay, so we map to S with sigma, right? Okay, and we have our sigma prime, use of the garbling, but here we're trying to show the second statement, right? So this is a map to S prime, and finally, okay, this has to map to set A. So A is the set of the actions, right? And similarly, S prime has to map to set A as well with alpha prime. Okay, and this is the diagram, but later we'll have to prove this, right? Actually, this is something we need to prove, that it really commutes, right? So if it commutes, then it's fine, but we have to prove that, right? Okay, so that's the second statement. So the third statement can be rewritten using the stochastic map as well, right? So we say that the expected utility of a strategy, so this only depends on this conditional probability over the actions, right? So this can be written as follows. So we have our utility A omega and times the alpha composition with sigma A given omega. Okay, so together, and we have to sum over all the A's, right? So together we have our prior belief, okay, and sum over all the omega. Okay, so this is the expected utility that we can rewrite using the stochastic map here. Okay, so right, so this utility depends on the action and state, and it's a real number, and P is the prior belief, okay, on the state. Okay, so we are ready to begin to prove the Blackwell theorem using this approach given by this study. Okay, so let's see how do we actually do this. Okay, proof. So from 1 to 2, this direction is very straightforward, right? So that is essentially saying that we are trying to, we're trying to use this to get here, right? To show that this diagram actually commutes. And that's very easy, right? Let's just redraw this picture and make it clearer. Okay. So we want to prove that the second diagram commutes, right? So there's a map to S. This maps to S prime, and they both maps to A. Okay, alpha. Okay, so what we know here, so this is alpha. We have statement 1 holds, right? Holding, which is holding. So that means we have this gamma function, right? Okay, so the thing left is actually we can simply complete the rest of the diagram by defining that a garbling alpha equals to gamma had the composition of gamma with alpha prime. Okay, so that's it, right? So that completes this this diagram, right? Then it commutes. So then the second statement is proved, right? So this is very interesting and very simple way to prove this. Okay, so let's do the other way around from 2 to 1. Okay. All right. So first we have now we use the idea of the identity map. Okay, just defined in the beginning. So we now here we define alpha to be this identity map. Okay, for the signal of the sigma prime. So this is the ID S prime. Okay. So if we have statement 2, so it means that there must exist an alpha that makes the their own diagram commutes, right? So the original diagram in the second statement. So it basically is this. So a map from S from omega to S with signal sigma. Okay, and map from omega to S prime with the sigma prime. Okay. And from S prime to S prime, this is simply ID S prime, right? Because it maps to itself with ID, what we just defined. Okay, but here from S to S prime, this is actually alpha, right? So that's what we defined. Okay. All right. So here the interesting part is that we notice that in this case we have something that sigma prime. So this is by the definition of the ID, right? Identity map, IDS prime, composition with sigma prime, right? So this holds. And additionally, this equals to the composition of alpha and sigma, right? Okay, because this diagram commutes, and this is given actually. Okay, so this is given by the commutes, right? Because because the second statement it holds, so this is true, so that we use that to prove 1, right? So that the this is given, right? So this commutes is given, and we have this green to be true here, right? We have this equation. Okay, so then what we have is this equal to this, right? So sigma prime equals to alpha composition with sigma. Okay, so that is essentially saying that alpha is a garbling from sigma to sigma prime. Okay, great. Then we proved statement 1 from 2. Okay, So that's the other way around. Okay, so now we have shown 1 to 2, 2 to 1. Next, we can show that 2 to 3 and 3 to 2, okay, to complete the proof. Okay. So now we have already used those diagrams, and next, between 2 and 3, we don't use those diagrams anymore, but we still use the some ideas from the stochastic maps. Okay, so 2 to 3. So here we fix this set of the actions, okay, and this utility function, and we define that. So the set of actions A and utility is U. Okay, so we define that lambda sigma. Okay, so this is set of all the distribution over the actions that are feasible under the sigma. Okay, so this is the set of all distributions. Okay, conditional probabilities, conditional distributions over the actions that are feasible. Okay, and this is under sigma. So specifically, this definition is essentially saying that the composition, right, alpha with sigma, and there's a map from S to the set of all distributions over the action space. Okay. So remember that we wrote the expect utility in terms of the stochastic map, right? In the beginning part, right here. Okay. All right. So here with this definition, okay, we can use this lambda to rewrite the composition here. Okay. So essentially, this decision maker is maximizing, and again, it's summation over the omega and A. But here, we also have utility. But here, instead of the composition, then we simply write this lambda. Okay, so which is a typical element from the space of lambda, the big lambda space. Okay. All right, and prior, of course. So this maximize over the lambda as an element from its space. Okay. So, and this direction is very so from 2 to 3, this direction is very straightforward, right? Because that we can see if lambda sigma, this set is bigger, so it contains the other one, contains lambda sigma prime. Okay, then we can immediately see that this decision maker can actually obtain a higher expected utility under sigma compared to sigma prime, right? So higher expected utility under sigma than sigma prime. Okay, and this is because that this set is bigger, is larger. So if we are maximizing something, and we're maximizing this thing here over the lambda, and this set that we can choose is actually bigger, right, than the other one. So it means that this maximized value, it has to be bigger than the other one, right? So this is very straightforward because we have more choices, and all those choices possible choices are already, all those choices from here are already contained here. Okay, so we have more possible choices here to actually for us to allow us to choose from more possible choices of the lambdas. Okay, to maximize this object. Okay, so that's the easy direction. Okay, and the only thing left is the other direction from 3 to 2. Okay, all right. So from their paper, and they're using the contrapositive argument to prove. Okay, so they first assume that if two is not true, okay, then if we can show that three, okay, so if two is not true, right? So because we're trying to prove that if three is true, then two is true, right? So if now if we assume that two is false, two is not true, then if we can also show that three is not true, right? So then that actually proves our statement, right? Okay. Okay, so if we assume that two is not true, then it means that there must exist this lambda prime, okay, and from their space, lambda subscript sigma prime. Okay, so the subtlety here is that, okay, because remember that in the second statement is that the one set contains the other one, right? So here, if we want to assume that two is not true, then we have to say something about a special element, right? So let's say that this special element is the lambda prime, right? So this lambda prime belongs to this set, but it does not belong to the bigger one originally, but here, because we're assuming that this is not true, right? So this lambda prime, we assume that it belongs to this set, but it doesn't belong to the other one, okay, without prime, the sigma without prime. Okay, hopefully you see the idea here. Okay. All right, so something that we're going to use is the separating hyperplane theorem, and we don't need to bother to actually prove that theorem, but we just use the result of that. Okay, so the condition to use that theorem is that we simply observe that this lambda sigma, this is a subset, okay, of the real with cardinality of a state space times the action space, right? Okay, so that many dimensions. So now we and it's also not hard to show that this set, okay, so this set is actually, it is compact and it's also convex, okay, so that we can use the sort of the separating hyperplane theorem, okay. And if this A has two actions at least, right? So it has to have at least two actions, right? So otherwise then this problem doesn't make any sense, right? So then this means that then we can use the separating hyperplane theorem. So there exists a separating hyperplane, so which is orthogonal to a vector. So this vector is something that we will use as our utility, okay? So this vector, okay, which is just the norm vector, right? If you know this theorem. So this vector is just element from this space, okay, with those dimensions. Okay, so then we can say that there's this norm vector, right, and there's a separating hyperplane, and which is orthogonal to this vector, right? So such that this point, okay, so this point lambda prime, this is actually, it can be separated from lambda. Sorry, not. So there shouldn't be, yeah. So this can be, yeah, this is correct. There's no problem. So lambda prime is then separated from all the lambdas. Okay, so that's what we want. Okay, so what we want to show that this special guy, because this guy becomes special, okay, so it belongs to lambda sigma prime, but not in the lambda, but it doesn't belong to lambda sigma anymore. So we want to show that this, if it doesn't belong to that, okay, there should be it doesn't belong to. Okay, so if it doesn't belong to that, then we want to show that this lambda prime will be separated, and it can be separated from all the possible lambdas. Okay. All right, and then how do we show that? So we just use the utility function to be our norm vector, and to show that there exists this separating hyperplane. Okay, so then specifically we can say that summation of this v a omega, okay, with with lambda a given omega, okay, and this is summation over all the omega and a's, right? Okay, so this is smaller than omega a, summation over omega a, v a omega times lambda prime a given omega. So this lambda here, okay, this has to be any lambda. It has to be, so this inequality holds for any lambda belongs to its space, okay, lambda sigma space. Okay, so then there must exist this kind of separating hyperplane to separate this lambda prime from lambda using the this orthogonal norm vector, orthogonal to this hyperplane. Okay, so actually it's separated by a hyperplane, but that hyperplane is orthogonal to the utility here. Okay, so that's the correct way to put this. So then we can say that this agent, if this agent is acting in Bayesian manner, right, then with this utility function v, and of course so we don't have a prior, so we assume that the prior here is uniform. Okay, so we because we can say that we can just the reason that we can assume the uniform here is that we can just find a counter example to show that to show something wrong, right? So that's enough. That's sufficient for us to prove this, right? By the contra positive argument. Okay, so then this is a uniform prior. So this is a subtle, and we don't need to bother to write it anymore. Okay, so uniform for both sides. Okay, so this agent, if this agent is Bayesian and is acting in a Bayesian manner, and with the utility function v, and also the uniform priors, then this agent can obtain strictly higher utility using this under this sigma prime. Okay, let's write it this way. So the agent, right? So in a Bayesian manner, with utility v and uniform prior, this agent actually can get a strictly higher utility under sigma prime. Okay, not sigma prime is higher than sigma. Okay, so here from the incorrect assumption, okay, because here remember that we start from something which is wrong, we assume that 2 is not true. Okay, then we show that here 3 is not true. Okay, so this means that 3 is not true. Okay, right? So together, so this is essentially saying that we can use 3, okay, to derive 2, right? So this direction then will be true. Okay,